So a couple of things you can do with your integration of the reciprocal function. You can find area between a curve and the x-axis. All you need to do is look between your upper and lower bounds, plug in y and integrate it with respect to x. So for example, let's say you were looking at the hyperbola y equals 3 over x. You've plugged in y there because y is equal to this. So you're integrating y with respect to x. Now we can also find the area between a curve and the y-axis. So if you've got a hyperbola like this, let's use good old y equals 1 over x, and you wanted to actually find an area in here, well, if you could call these upper and lower bounds a and b, we can actually integrate between those bounds and just going the other way around, instead of finding y dx, find x dy. Now, the thing you've got to take into account is that this formula is in the form y equals something. Before you can put x in there, you need to rewrite this so that it's x equals something. Easy way to do that is multiply both sides by x, divide both sides by y. This same curve can be written as x equals 1 over y. It's the exact same thing, just looks a little bit of a different form. Now you could plug in, let's say our bounds were, I don't know, 1 and 2, and you could put x in there. Now you won't write x because you can't integrate x with respect to y. It hasn't got any y's in it. You have to write what x equals. And you can do this just the same way as we've already been doing with the x's. 1 over y dy is the same as 1 over x dx. It will integrate to become a log. And the other thing you can do is you can find the area between two curves. Now, assuming that one curve is higher or taller than the other one between your two bounds, all you need to do is do the upper one minus the lower one. You can put them together and make one function out of them and integrate them all in one go. So here's an example of finding the area enclosed by two curves. Now, they haven't let us in with much here. We've got quite a lot of the work to do ourselves. We need to work out where in space this is happening and what our bounds are. Also, both of the curves, as you would say, even though this one's a straight line, haven't been written in a form that we're used to. We're used to seeing y equals something, and neither of them are written that way. So I would start by just writing them around the other way, y equals, and dividing both sides by x here. Now this first curve looks much more familiar to me. I know that it's a hyperbola that's just a little bit fatter than the normal one. And this other one here, I've got y equals, and I subtract x from both sides, and I've got minus x plus 3. Now a sketch is really useful here, just so that I can see exactly what's happening. Y equals minus x looks like this and goes through the origin with a gradient of -1. But my straight line goes through the y-axis at 3. So it comes down like this and goes through here also at 3. Now I've got my hyperbola, which obviously has two arms on it. It's going to come down somewhere here, and I'm not sure exactly where it's going to cross over. This arm isn't going to cross this line ever, at all. Now the fact that they're saying that there's an area enclosed tells me there must be a sneaky little area in here that is enclosed by the two, otherwise they wouldn't have asked me to find it. And to work out what I need to do, because after all, when you first look at a hyperbola like this, you might wonder if it comes out this way, or whether it actually does tuck in and enclose. Well, I can verify this algebraically now by finding this intersection point here and this intersection point here. And I don't necessarily even need the y values of the intersections. I just need to know what the x values are, because those are going to be my bounds, a and b. All right, how do you find intersections of two curves? You solve them simultaneously. Now that I've got them both written as y equals this and y equals that, I can say that this must equal that at those two intersection points. So we've got 2 over x equals minus x plus 3, and now I need to solve this, and I'm looking for two answers. Straight away that warns me I'm probably going to have to solve a quadratic, and I have 3 methods for that. I might be able to factorise it, I might be able to use the formula, or I could complete the square. Now it doesn't look like a quadratic yet, does it? But also, I don't want fractions to deal with. How do I get rid of this divide by x? multiply everything by x. So multiplying this by x, multiplying this by x, and multiplying this by x, now it's looking more like a quadratic. I don't like solving ones that have the minus in front of the x squareds, do you? I much prefer it if it's just x squared, makes it way easier. So I'm going to add x squared to both sides and subtract 3x from both sides so that I have everything on one side. Now it's looking quite straightforward. Can I factorise it? I need factors of 2 that add to minus 3. They must both be negative. So I can use minus 1 and minus 2. That means that x must be 1 or 2. And that looks about right, because if this is 3, I had a suspicion that they were going to be somewhere in there, didn't I? So now I can actually fill these in, and instead of putting a and b, I can put 1 and 2. Does it matter that my graph isn't perfectly to scale? No, I've been asked to find an area. The fact that I've drawn something at all, that's my business. That's part of my working. And your graph doesn't have to be to scale. It's showing something that's mathematically sound, even if the scale isn't perfect. All right, I'm ready to go now with what I want to find. Just to make a little bit more room, I might get rid of my picture. No, I can just work down here. All right, to find the area, it's going to be positive, isn't it, this definite integral, because it's sitting above the x-axis. So I'm just going to hook straight in and write area equals confidently, knowing that it's going to be the integral between 1 and 2 of, remember I have to do the upper curve minus the lower one. So which one's the upper one here? It's the straight line, isn't it? Because it's the tallest between these 2 points, and the curve is the low one. So my upper one, I want to put it in the form of y equals something, which I have here. That's the part that I need to integrate. Minus x plus 3. And now I need to subtract the other curve, which is my 2 over x. And now I can integrate that whole thing in one go, just working one term at a time. All right, next line, square brackets. How do we integrate minus x? Well, if you had x, it would be raise the power by 1 and divide by the new power. But we've got minus x, so that constant of minus 1 just stays up front. Every time you integrate, differentiate to check that you get back to where you started, just to double check it. The 2 will come down the front if I differentiate. It'll cancel with that 2, and I'll have minus x. Perfect. All right, integrate 3. We get 3x. And again, double check. When I differentiate 3x, I get 3. Good. And this one, we've learned how to deal with 1 over x. It integrates to become the natural log of x. So 2 over x is just going to give us, whoops, I need a minus, that constant out the front. I'm going to have 2 lots of that. Okay, now if you need to do some working on the side just to check that out because it seemed a little bit dodgy or a little bit hard to do in your head, think through what that would be on its own. That's the same as this, and that's the same as 2 lots of that. We've got that negative and that stays, so we're good. And we've got our bounds, 2 and 1. Now there's going to be 6 bits because there's 3 parts here, and I have to sub 2 into all 3 parts, and then do a takeaway sign, and then sub 1 into all 3 parts. So I'm going to have a big long line of working here. I like to think that through just so that as it gets long, I'm like, yeah, that's all right, I expected it to be long. It's all good, just keep going. Anything I can easily do in my head, I will, but if it looks too tricky, I'll just write it down and leave it for the next line. So subbing 2 in here for x, it's not minus 2 squared, it's minus 2 squared. So square the 2 first to get 4. 4 divided by 2 is 2, and that minus is just hanging out the front, so we've got minus 2. That's a place you could make a mistake. All right, next thing, we need to sub the 2 in here, so 3 2s are 6. And we need to sub the 2 in here, so we've got minus 2 natural log of 2. Minus, now we need brackets so we don't make a sign error when we sub the 1 in. Subbing in the 1, I've got 1 squared is 1, so I've got minus a half. And subbing in the 1 here, I've got plus 3 and minus 2 lots of that. Now, things that you can easily spot, as I'm writing this one down, I'm thinking e to the power of 0 is 1. So that whole part here is 0, and minus 2 lots of 0. I'm just going to cross that out, because that's 0. Okay, that saves me rewriting it. Now I've got some tidying up to do. I don't want to make a sign error with these two guys. So easiest way to do it is probably think about what you've got in the brackets here. I've got 3 minus a half, so I've got 2.5 in this part. So I've got minus 2 plus 6, that's 4, minus 2.5, that's 1.5. So I've got 1.5 or 1.5, write it however you like, minus this. And that's nice and simple. There's no need to play around with that. That's done. You can put 1.5 or 1.5 or 3 over 2. They're all the same thing. Now we're dealing with area, so are we finished? Not quite. This is how many units square we have, and you can just write u squared for units squared.